All right, welcome back. So as we continue our talk on IR spectroscopy today, we want to remember the three things that we're going to be talking about: wave number, intensity, and shape. These three characteristics are going to help us identify what type of functional group is present in our unknown molecule. Speaking of wave number, frequency or wave number for a stretching vibration is dependent on two things, and we kind of hinted toward this last time: bond strength, right? What two atoms are being held in what kind of way, double, triple, or single bond, and the mass difference of the atoms. All right, so again, looking specifically at the two atoms that are bonded together. This is the calculation for wave number, right? Remember, this is wave number. And it's very complicated if you look at it, but what we're just doing is dissecting and being able to predict where these stretching frequencies are going to show up, right? So the force constant is in the numerator. So bond strength in the numerator, what that means is as bond strength increases, think about what's going to happen to the frequency or the wave number. Wave number also increases. Notice how they're proportional. This is in the numerator, so as one increases, the other increases, right? Reduced mass in the denominator. So the larger the atoms, right? Technically, in that denominator, the larger the atoms correlates with a lower wave number. Smaller reduced mass, smaller atoms, higher wave number, right? Looking at that denominator being inversely proportional. So a couple of things that we need to think about: stronger bond, higher stretching frequency; larger mass difference, smaller the atoms, right? Higher stretching frequency. What that's going to mean for us is typically carbons and hydrogens, or things with hydrogens, are going to appear at a higher wave number, right? Carbons to hydrogens typically appear around 3,000. Carbon to deuterium, we didn't do a lot with deuterium if you were in my section for the first semester organic chemistry, but we're going to do a little bit more with it today. Deuterium is heavy hydrogen. It's hydrogen with one proton and one neutron, right? So it is a mass number of 2. One proton, so it's hydrogen, right? But it has an extra neutron. It's an isotope of hydrogen. So it's called deuterium. It's given a special D symbol. That is a heavier atom, right? So it has a lower frequency. Same thing when we see oxygens to carbons, chlorines to carbons. Again, looking at our second identifying here, triple bonds appear higher than double bonds are higher than single bonds. So again, just whittling down a very simplistic type of structure here. Bonds to hydrogen appear at the far left, the highest wave numbers, then the triple bonds, then the double bonds, and then all these single bonds. That type of description here of where these typically show up is based off of the calculation. No, you don't need to calculate. Yes, you need to know the two types of characteristics here to establish a wave number and be able to represent these across the board simplistically. Hydrogens, then triple bonds, then double bonds, then single bonds. All right, one more thing. When we're looking at that range from 400 to 4,000, we will only be looking at the range of 1,500 to 4,000 centimeters to the -1. Below 1,500 is the fingerprint region. It's very, very difficult to analyze, so we usually don't do it. What we want to actually analyze is the diagnostic region. This region above 1,500 centimeters to the -1 is more clear, and it provides a better picture as to what our compound's functional groups are. So single bonds, very, very difficult to decipher. Double bonds, triple bonds, and bonds to hydrogen, much easier. Because molecules might have the same type of covalent bond, things like this, 2-butanol versus 2-propanol, virtually the same IR, not the same compound though, right? We have C4 versus C3 here, right? And we have different numbers of hydrogens, and we have an oxygen here. So when we're looking at this compound, looking at their IRs, they're almost indistinguishable, right? These two are almost the exact same. Yes, the fingerprint region right here looks different than this one, right? And that's where if you had a fancy computer attached to your IR spectrometer and you could look in a database, then that's helpful. But again, be very careful with these. We're going to try our best to just analyze the diagnostic region. I will always give you a molecular formula when I want you to decipher the actual structure. And also usually IRs are just matching. We'll see that in class. Now, comparing the stretching frequencies for different types of bond lengths, right? And bond strengths. So sp3, sp2, sp carbons, we know that those orbitals get smaller, the more s character, right? The sp hybrid orbital is smaller, and therefore this bond is stronger. Excellent. Then the sp, a little bit longer bond length for sp3, right? So sp3 is a longer bond, so it's a weaker bond. sp is a stronger bond, it's held a little bit tighter. Now, that stronger CH bond of the sp hybridized carbon to H has a higher stretching frequency. Again, these are just giving you the numbers, giving you the characteristics. What we see there is typically the best thing to do when given an IR is draw a line right at 3,000. If you're less than 3,000, all you have is sp3 carbons to hydrogens, right? If you're just above, there's your sp2 carbon to hydrogen. And if you're really far above, there's your sp carbon to hydrogen. So utilizing this image, 30,000 is the general number for CH bonds, but looking at the hybridization, we do see a spread across around 3,300 to 2,800. All right, it is possible to have a carbon-carbon double bond or a carbon-carbon triple bond that does not have any CHs, right? So just because you don't see anything above 3,000 doesn't mean you don't have that hybridization. It just means you don't have the carbon to the hydrogen, right? So remember, hydrogens to atom bonds appear above 3,000 or 2,800 to above 3,000. Doesn't necessarily mean you don't have that type of carbon. So looking at fully substituted carbons, carbon-carbon double bonds, or fully substituted carbon-carbon triple bonds, very important to note. Resonance, what does resonance do? Well, again, with resonance, what actually happens is it lowers the wave number, right? So when we're looking at these two wave numbers, a ketone versus a conjugated ketone, what's the difference here? Great question. Resonance makes the bond a little weaker, the pi bond, right? The p bond. When we're looking at that stretching frequency, we're looking at the characteristic of the carbon-carbon double bond. In a conjugated system, when we have resonance, what happens is there's more resonance structures without that carbon-carbon or carbon-oxygen double bond. So what happens to the actual wave number is it gets less, it gets lower. So anything with resonance technically will have a lower wave number. Now, when we see a couple of different carbonyls, which we will definitely get to once we start chapter 19, 20, and 21, conjugated carbonyls have that lower stretching frequency. The same thing happens whether it's a ketone or an ester or an aldehyde, things like that. So just because this carbon group changed to an ester, right, an OR group, doesn't mean that the conjugation idea changes, right? So anytime you have conjugation where you have two adjacent pi bonds, that conjugation, that resonance will decrease the stretching frequency. Let's talk about intensity next, all right? The strength or the intensity of the signal can vary. When we're talking about that, we're again talking about the y-axis here, weak signal versus strong signal. What do we see? Well, when a bond actually oscillates, it's undergoing a change in its dipole moment, right? So the dipole moment includes the distance between the partial charges. And so oscillating that dipole moment creates an electrical field to surround the bond. Yes, there's a mu is equal to E times D. We don't need to know that calculation. But what we do need to know is that the more polar the bond, the greater the opportunity for that change in the dipole moment, right? The interaction between the waves of the IR radiation and that of the electrical field of polarity. So greater the bond polarity, stronger the IR signals right there. Because oxygen to carbon is polar, its dipole moment is already large. A carbon-carbon bond is not polar, and so it does not have a large dipole moment. We would have called that a non-polar bond, looking at that carbon-carbon double bond. Carbon-oxygen double bond, polar, greater or stronger, more intense signals on the IR. We can see that in the general length between the carbonyl and the alkene, right? Carbon-oxygen double bond, also called a carbonyl, carbon-carbon double bond, also called an alkene. Again, very, very important here, just some random things that happen. If a bond is completely symmetrical, then the stretching frequency is not observed in the IR spectrum. This has to do with the idea of symmetry and non-polarness, right? And there's a complete non-polar molecule here in this tetramethyl alkene. So looking at the absence of a signal is also very, very important for us. So not only are we going to be looking at the signals, we're also going to be looking at the absence of signals, right? What you see and what you don't see is always going to be important. Last one, shape. When we talk about shape, we're talking narrow versus broad. Broad typically occurs with OH stretching signals. So when we're looking at this broad signal right here, this is a very characteristic OH stretch. Narrow signals are usually reserved for NHs, CHs, carbon-carbons, things like that. Why is the OH so special? You guessed it, hydrogen bonding. The hydrogen bonding that occurs actually lengthens this bond right here, that OH covalent bond. Now that is not an arrow for a dipole moment. This is a lengthening. Imagine that oxygen on the right is actually pulling the hydrogen towards itself in the hydrogen bond. Here's our H bond, the intermolecular force that we all know and love. That hydrogen bond is literally pulling the covalent bond of its adjacent alcohol molecule and thus weakening it. And so as a result, what we actually get is a bunch of different types, varying strengths of OH bonds in our sample, dependent on where is the length of the OH bond, the covalent bond, based off of the hydrogen bonding that's taking place. But the OH stretch signal will be narrow if we use a dilute solution of an alcohol, and if it's prepared in a solvent incapable of hydrogen bonding, right? So very difficult to do, but it is possible. And what that usually looks like is this. We do see that there is a stretch or a broadening of a little peak and then a free OH peak. And the free OH peak would be one that is free of hydrogen bonding. When it's dilute, it can look like that. When it isn't dilute, or when there's too much alcohol, or if there's a solvent that you use that is a polar solvent, doesn't need to be polar protic. Technically, it could be a hydrogen bond participator if it has an oxygen or a nitrogen or a fluorine in it, right? So any hydrogen bonding capabilities, you'll see this broad signal. Typically for our in-class practice problems, we see broad signals. Hydrogen bonding also occurs in carboxylic acids, which you see on the right-hand side participating in hydrogen bonding. Hydrogen bonding here and here. This is what we would call a dimer. Dimer, two molecules reacting together. Notice how broad this OH stretch is from the carboxylic acid. It's just like, hello, I'm a carboxylic acid. Why it's pokey right down here? Yeah. Why it's narrow right down here is because this most likely is from our CHs overlapping with the OH from up here, right? OH is the broad part and it's overlapping, it's expanding past 3,000 rather than staying put at 3,400 centimeters to the -1. Now, that is from a specifically carboxylic acid because the hydrogen bonding is more pronounced because of the two locations of hydrogen bonding. Dimer meaning two molecules interacting together. The only time we also saw dimers last semester was when we talked about hydroboration oxidation and how BH3 technically forms dimers with itself. Now, signal shape for amines, nitrogens to hydrogens, amines. Typically, we'll see primary and secondary amines exhibit NH stretching signals. Tertiary amines do not show that NH because remember, a tertiary amine is going to be one with 3 R groups. So let's just remember our primary, secondary, and tertiary idea. It's counting up the number of carbons that are on the nitrogen itself. So a primary amine means it has 1 carbon and 2 hydrogens. A secondary amine means it has 2 carbons and therefore 1 hydrogen. A tertiary amine will have all carbons, so no hydrogen. So we wouldn't see anything in this upper range around 35 to 3,400. Now, for every hydrogen, we usually see 2 signals, or for every hydrogen, we see the 1 signal, excuse me. So for a primary amine, we will see a signal for each hydrogen. For our secondary amine, we see 1 signal for that 1 hydrogen. They are broadened a little bit, but not as much as the OH. Again, 2 NH bonds can vibrate in 2 different ways. There's the symmetric stretching, where they go out and in at the same time, or they can do asymmetric stretching. And so that's why we see 2 signals. It's not technically 1 per hydrogen. It's based off of the combination of stretching. Half the molecules are stretching one way, the rest of the molecules are stretching another way. So to analyze a spectra, we're going to look at table 14.2. You can look it up in your textbook now, but we're going to look it up together. And we are going to focus on the diagnostic region. We're going to check for double, triple bonds and atoms to hydrogen. And we're going to look at the wave number, the intensity, and the shape. And that's how we are going to identify what we need to know about the molecule's functional group. I like this chart too. I'm a big chart or conceptual mapper. Whatever works for you is great. I like to give you a couple of different ways to look at these concepts. But again, this one is a really great chart in your textbook. When looking at the 2,700 to 4,000 region, that's the hydrogen to atom region, draw a line at 3,000 and focus on what signals come around it, right? And be able to identify these 5 functional groups from that range. We have learned numerous reactions previously, and I think that's the biggest thing that I want to take home from first semester organic chemistry. We will be in class use IR to distinguish between two compounds as well as understanding an unknown compound. But IR spectroscopy at the end of the day is used by organic chemists who say, hey, I want to take cyclohexanol and I want to make cyclohexanone, right? I want to take an alcohol and make it a ketone. How do I know if I did it? Clear liquid, making a clear liquid? How do I know? We typically use IR spectroscopy for that. So that's what we're going to be at the end of the day trying to use IR for. Not only is it to decipher unknown compounds, but it is to distinguish between reactants and products. How do we know when our reaction ends? Excellent.